The eclipse on Mars is going to be a fun article to hear about.
There we go. There we go. I feel like we're live. Oh, I should get the chat. Oh, I should get the chat. Okay. Yeah. Did you see those really cool pictures from Mars Express of Phobos? Came out like maybe 2 weeks ago. Maybe 2 weeks ago.
Yeah.
And they actually had to reprogram the camera on Mars Express to be able to take a picture that close. They'd never expected that they were going to get that close to a target. And so it's an awesome story to hear how they did it and then to actually see the pictures, because it's like the nicest pictures of Phobos we've seen so far.
It's pretty awesome.
Until the lander shows up, until the Japanese, until the Mars Moon
Explorer, MMX, right?
Explorer,
MMX. Mars Moon Explorer. Yeah.
Until that mission comes, and it's just going to be bringing like a battle fleet of rovers and landers and small caliber weapons and
true JAXA form.
Yeah. And it's just going to begin an exploration of the Mars moons, the likes of which we've never seen.
It's going to be really.
I know I rave about them every time, but
debates.
Oh yeah, I mean, are they made of Mars or are they captured potatoes?
Are they coated by Mars? Are they? Yeah, whole bunch of stuff. Yeah. Right now, it's a little bit of a free-for-all where they could be anything from Mars mantle to Mars surface to captured random asteroids, coated or not coated by Mars. It's really, it's pretty open-ended.
So apparently, we're out of sync, Pamela. Like, not that you can fix this.
Sorry, I just realized I heard snoring and looked down, and a cat had somehow snuck in and is under my.
So maybe it just the internet just needs to warm up. But it's definitely not coming from me, because now I've got my gigabit internet.
Gigabit. I saw that on Twitter. That looks very cool.
Yeah. You mentioned it on Monday. I was very excited for you.
Yeah.
And then YouTube decided to be all YouTubey.
Yeah, so normally when I record the videos for the editor, and it takes me about 8 hours to upload the video once it's done, and it took me 4 minutes. So I was like, normally I talk to the editor, and then he's like, okay, well, I'm going to bed, and I'll download it in the morning when I get up, and I'm like, it's done. And he's like, or I'll download it right now. It's ready to go. So
wow, this is the opportunity over Thanksgiving to like stream all the movies.
All of them.
Yeah.
If only we hadn't already celebrated it a month ago. But maybe I could go back in time or something.
I think there's a movie about that. In fact, there may be.
Is there going back in time? A Canadian going back in time a month to celebrate American Thanksgiving?
No. Although my wife does give me flack about that every year.
Yeah.
Oh, my husband too. I mean, he's cooking it. He's going to be cooking for tomorrow, but he continues to say like, "No, I already celebrated Thanksgiving."
Yeah.
Last
month.
Yeah. Just like a reminder again that this is suboptimal. That the best time to have Thanksgiving is in early October, and let me tell you why.
Because you're really far north. And the fields are solid by November?
Yeah, because the weather is better. And so trying to travel in mid-October is a lot better than trying to travel in late November.
What is your weather right now, Fraser?
It's a big country.
I know. I'm just asking about what yours is right now, because I know what Nova Scotia's is. So
mine is sort of foggy and 6 degrees. So
I would just like
it's warmer there than in Halifax.
Yeah, I'm sure. Yeah.
Down here in Florida, it's a really good thing to wait to celebrate Thanksgiving till the end of November, because that's when hurricane season's supposed to be over.
All those rules don't count for Florida.
Well, Florida hardly ever makes sense. So
and California, when I say it's cold here, I always try to explain that it's California cold.
Relatively,
but I think for most of the U.S.,
72.
It's not well, okay, it was up at 70 today, but that has been this is the warmest it's been in like 3 weeks too. So
all right, let's get started. Hello and welcome to the Weekly Space Hangout for Wednesday, November 23rd, 2022. I'm Fraser Kane, the publisher of Universe Today. This week, we're going to be talking about Webb seeing so much exoplanet atmosphere, an asteroid that was precisely predicted where and when it would strike the Earth, a partial solar eclipse on Mars, and of course, Artemis I goodness, and an update on Mars rovers. Joining me this week, we've got Beth Johnson. Hey, Beth.
Hello, Fraser. How are you?
Good. We've got Dr. Nick Castle. Dr. Nick.
Hey, Fraser. How's it going?
Good. And we've got was once a guest and has now become a regular, Dr. Paul Byrne. Paul, welcome back.
Hi, Fraser. Good to be here. Thank you for having me back.
And I just feel like this is just an amazing gift to be able to chat with you some more. I'm really looking forward to this. Now, before we get into this week's stories, I want to give a huge shout out to our good friends and fans at the Weekly Space Hangout crew. They're executive producers of this show. They call the shots. We do what they say. So if you want that kind of ultimate cosmic executive power, join the Weekly Space Hangout crew. Go to wshcrew.space. And now that perhaps various social networks are starting to come apart at the seams, you may want to look for a community that is wholesome and engaging and wants to talk about space. And there's no better place than the Weekly Space Hangout crew. So wshcrew.space. Now, we have an interview with Dr. Victor Gysembergh, and I screwed up. So I didn't record my audio for the interview, but we recorded his audio. So at the end of the show, we're going to play the pre-recorded audio, and assuming we can figure this out, I'm going to do a voiceover of myself asking the questions. I've written down what all my questions were, and it's going to be hilarious. So enjoy. So when we reach the end of the stories for this week, stick around for the interview, but also just really enjoy my tremendous screw up. But the story is amazing. So, in fact, this is your story, Beth, I think, about discovering, was it yours? No, maybe not. But Hipparchus. So it's about them finding ancient Hipparchus writings in an old document. And now
not mine.
No, that wasn't you. No.
Sounds
it's
cool,
super cool. Yeah, it's kind of amazing. All right, well, let's get into the news. So obviously, big news. More updates on Artemis. Last week we talked about the launch. How is Artemis doing?
It seems to be doing really well. I put up a couple images to go through on the slideshow, just in case you happen to be asleep for the last week. Yes, it finally launched. I'm sorry, Fraser. I was wrong. I owe you something from whatever that pool was that it didn't launch on Christmas. I'm actually happy to be wrong about this one because it didn't roll into holiday for a change. But the launch went off without a hitch. It was actually surprisingly smooth. There was a launch delay of, what did it end up being, about 40 minutes in the launch delay, but that's nothing as far as a launch goes, especially for the prototype vehicle, the first launch of something. So in terms of what does the mission look like, can we put up the slide that shows the whole mission profile? That one. So this is a wonderfully complicated mission compared to what Apollo was designed to do. Apollo pretty much did a figure eight there and back again. What this mission is doing is it's going out to the moon, looping around it with a really close approach, very, very near to the surface. It's actually done that part already. And it's between points 9 and 10. The green line is the outbound, the blue line is the back. And 10 is where it injects into a very slow retrograde lunar orbit. So that's coming up on Friday. So that's when they're going to burn to make sure that they orbit the moon the way they're intending to. If you want to watch live updates on this, NASA actually has a tracker that shows you exactly where things are. But true to wonderful form, it's in a totally different projection from this. Do you have the next? I forget if it's the next slide or the one after that. Yeah, this one. So what's going on here is we're seeing the whole thing with the moon tracking around in its orbit and Orion tracking around in its orbit, instead of saying, let's keep the moon and the Earth fixed in the diagram and show just how the spacecraft moves relative to that two-body system. But this, as of actually about an hour and a half ago, is exactly where the Orion is relative to the moon. So it's past the moon in front, it's going to loop around back behind to enter into its main orbit. And from the perspective of keeping the Earth stationary, the whole mission is basically just coming past the moon, slowly going outside of lunar orbit, slowly coming back by the moon, then being winged back into Earth orbit. Those tight inflection points are where it uses the moon's gravity to sharply change orbit after a burn.
We got a great animation last week from Morgan showing that how it just kind of kicks around the moon at one point, goes far away from the moon, and then comes back and then just drops straight down to the Earth.
Yeah.
Very clever orbit.
It's one of those things that if I'd done this in Kerbal Space Program, I'd just be cheering like, I broke it! I won! But yeah, it's awesome. It's also going to be the furthest out that a man-rated spacecraft has ever been. So, I mean, yes, this is the test launch, but this is intended to obviously launch astronauts to the moon in the future. And this will be the first out by a decent margin that any spacecraft like that's ever been. Now, there was one kerfuffle very, very early today where the tracking network lost contact with Artemis. There hasn't been anything published by NASA about what happened, and the outage was 47 minutes long, which honestly, if you have to troubleshoot a problem, isn't long at all. And they solved it by an engineering update on the ground side. So that suggests it may be the Deep Space Network having a hiccup, which is one of the reasons why you shake down these systems. Make sure that everything's going to move smoothly before you put people on it.
It's definitely scary. I've been waiting for whatever is the moment for, some kind of technical snafu, and here it was. This one definitely wasn't that scary.
I'm very
Pamela, do you have the launch? So we did a live stream of the launch, and we were all whining about how it sucked. Oh, we can hear it, but we can't see it, Pamela, or maybe we can.
1. Boosters in ignition.
Here we go.
And
why were there no cameras on the rocket? Why were there no cameras on the SRBs? Why weren't we getting this new modern 4K?
7.
Like, I don't want to sound like a conspiracy theorist, but I was kind of ranting a little.
3.
But now we got it. Check this out.
We are really spoiled by SpaceX.
And liftoff of Artemis I. We rise together back to the moon and beyond.
So there are 16 cameras just on the Orion capsule.
All 4 RS-25 engines on the core stage and 2 solid rocket boosters now propelling the vehicle at 128 miles per hour.
And then a whole bunch on some other spots. One's looking back down, one's examining the core stage, and then a bunch internally, which have been sharing a bunch of pictures. They've got a bunch that are in 4K. It's got terabytes of storage on board. It's
heck of a downlink.
Constantly disgorging all of this video content onto its local storage, and you know that when this thing returns December 11th, we're going to get that actual footage. Sirius K. Lee is saying, I missed the altimeter and speed readouts too. Yeah, that's SpaceX again has absolutely nailed this. Yeah. Well, yeah, NASA just placed an order for Orion, the Orions for 6, 7, and 8. So we know that they're at least that far into the future. So I think Yeah.
It
Yeah.
is.
Yeah, it really is.
There are a couple other pictures
I
You mentioned some of the cameras out on the solar wings. This has been really fun to watch, as what some of these cameras look like. There's one that shows Earthrise, although unfortunately the side of the moon facing the spacecraft was in the dark, so it didn't quite replicate the iconic picture. But one of the other ones shows the moon near close approach. What's really exciting from science points of view is this is a heck of a camera suite that we set along with this thing. So we're going to get some just amazing images down from it. And amusingly, you can see all of this on NASA's Flickr page for Artemis I. So they're releasing some of the images there is just a great place to look to see what evolves up there.
Yeah, and I think aren't they doing a live stream as well right now?
I believe so. Yeah.
They weren't. I got the impression from what I read that they weren't planning to, but they found they had that bandwidth in the DSN, so they're doing the live stream. I mean, it doesn't make for compelling viewing all the time because like right now stuff isn't moving that fast, but it is cool that that is a thing up there.
Every time I've gone to look at that live stream, it's been down.
Hey, it's a shakedown test.
So. I know. Come on, it's got to go to space.
Yeah, exactly.
And back. Yeah, it's sort of a similar thing. Like I don't know if you saw, well, like when NASA put a camera system or a live feed from the International Space Station, and same thing. Like every time I went to go watch it, it was down. But
Fraser, that might just mean that you're cursed.
Maybe, possibly.
Maybe it was before you got your fiber installed, right? But now you don't have that problem.
Right, yeah. Beth, you were going to say something.
I was just going to say I was deeply amused when you were doing the live stream and watching it. It's how like we were all sort of like, okay, it's taking off, and then nobody really like cheered like we usually do for rocket launch. We all just kind of sat there going, "What's going to happen? Is this going to fail?" Like we're just waiting for the big kaboom, you know?
Yeah. Well, like, what is the momentous event in a launch like this, right? Is it when the thing takes off from the ground? Well, not exactly, because it could still go wrong. Is it when the SRBs detach? There's more to come. Is it when the core stage detaches from the Orion capsule? That's getting close. Is it
for me
when it's in orbit? Well, now it's too late. You should have been cheering a long time ago. Now you're sort of relieved and it's over.
Yeah.
So,
for me, the defining moment of it's over and it was great was when Engine 3 posted to Twitter before Twitter went to a dumpster fire that said, "I made it! I'm done!"
Yeah, it is true though. We just I think when you watched the Falcon Heavy return and you saw the two rockets come back down side by side, that was a moment that you cheered.
Mm-hmm.
But when I see like the core stage detach, I'm just thinking, oh, those RS-25 engines going into the ocean. Oh,
yeah. Well, it's like you just see the dollar signs. Like, just
actually, what they could do is they could do, in addition to the altimeter and the speed, they could have dollars. Just kind of wrapping up like each thing, how much an SRB is, how much an RS-25 is. Yeah. But I will say this. Okay, so it didn't explode, so that's good. And you're right. I mean, this is the sort of thing where you're going to be on tenterhooks until we know this thing worked. But it is worth pointing out that SLS did perform effectively flawlessly. Now, we got to wait to see what Orion does and how it comes back and all of its systems do. I mean, that could have been one of the largest non-nuclear explosions in human history. And it wasn't. And so I guess that is something to be
Next, let's put humans on top.
You just have to decide, like, at what point you go, okay, it's not going to explode. And I think that was where we were all just sort of waiting. Like, now?
If you are looking for explosions and damage, one of the few headlines that I've seen the past couple days about Artemis was that it literally blew the doors off of the launch pad. So,
Yeah, so we had a couple of camera people at the launch. We had 3 people operating cameras. And they were instructed to not take pictures after the launch. So they could take pictures of the launch, but to not take pictures of the launch gantry and stuff afterwards. And we were all like, what's this about? Like, are they worried the Russians are going to steal? No, they wanted to sort of figure out the damage on their own. So
So the news highlight was that literally the doors on the elevator that transfers people from the ground up to the crew level of the rocket is still not functioning because, well, the doors were literally blown into the building. And there's a couple nice little pictures making the rounds on the internet with just sort of skewed door frames, and
they've just posted a whole bunch of these pictures onto the. If you go to images.nasa.gov, you can see all of the wreckage from that, as well as that video clip that we showed. So, congratulations to everyone on Artemis! Woohoo! There's the cheer.
Yay! Here's our cheer. Woohoo!
I just feel I'd be remiss if I didn't say the damage was actually mostly anticipated. So this isn't like, oh, it blew things up. It was like, oh, yeah, we knew that was going to happen.
Oh, okay.
And you know what? Let me just finish before we move on. I want to say one thing. Yeah, I wasn't cheering, but I did say I got goosebumps watching it live. The speed that rocket went up the tower.
Yes.
Once those SRBs kicked in, and I had a brief discussion of this on Twitter with people. I find SRBs quite frightening. I don't like them. And once those things went off, and you can see in that video we saw a few minutes ago, you could see the shockwave go through the plume. That thing just went up the tower much faster than the shuttle stack did, or Apollo that a Saturn V.
Yeah, it leapt off the.
It did.
It really leapt off the launch pad. Yeah. And we even remarked on that during the live stream. We just couldn't believe that it just jumped off that and was off and away. So, there we go. Pamela's sharing a broken door image. So, oops. Oh well. They'll fix that for next time. All right, let's move on. So, Beth, let's talk about this exoplanet atmosphere.
Yeah. So, they have JWST's up. It's running. We all know this. One of the preview images, I use the term loosely, was of WASP 39b, which is a hot Saturn really close into its star. And it was, there was all these amazing images that were released, and then there was, a spectrograph of it's like, okay, there's an atmosphere. We can detect this stuff. And everybody went, that's cool. Look at all these other pictures. But it turns out that was just the start of things. And so they just released, and when I say they just released, I mean there are 5 papers, 3 of which have been published, 2 are under review, and I'm pretty sure I got at least 7 or 8 different press releases from different organizations.
They were a big part of Archive that day.
They were, like I use AWS's site, and it was just like list. I was like, okay, so big story, so they've done an extensive analysis on the atmosphere of this hot Saturn, and they have found water, sulfur dioxide, carbon monoxide, sodium, potassium. They have detail all of this. They think they found cloud structure. They're looking at photochemistry. There's so many things to this. I mean, like, we could make a whole episode out of it. I think it's going to be, once all of the papers are out and everything's really been looked at, I think it's going to be kind of an amazing, huge story. So right now, for me, it's just sort of like a surface, like, what is all of this? Because it literally came out yesterday, and I'm still sort of wrapping my head around all of the information.
And many of these have never been detected in an exoplanet atmosphere before.
Yeah, I mean, this is what we were. This as a person who has been following exoplanetary science from the beginning, this was sort of the holy grail of JWST for that sort of thing. Was we wanted this to go up, and we wanted great, pretty pictures. Hubble's been giving us pretty pictures for a long time. We wanted exoplanetary atmospheres in detail, and we can do it. So. For me, WASP 39b is really just sort of that. It's beyond the proof of concept from the early science release part of it, and it's now just seriously look at all of the things that we can now detect within an exoplanetary atmosphere, and we can really do this to detail. And as someone who's also involved in SETI, like, that gives me hope for how we might be able to do searching for some sort of atmospheric biosignatures later.
And it feels to me like this is one of the first pieces of science that has gone through the whole process. Like, I think people don't realize, like, most of the observations that JWST has been making are in the hands of the scientists while they consider it, while they study it, while they prepare their papers and they publish them. And there have been, so far, I mean, it's only been a couple of months. It's been July since these observations have been going. When you look at the list of things they've been looking at, they're really exciting, and yet it's going to take. They've got up to 12 months to crunch this data before they finally release their data goes out to the public. But that should give them time, and so this is what it's going to look like for all that other stuff. Is what you saw today or yesterday with this exoplanet atmosphere, like a full court press of the announcement. And so I think a lot of people have felt very underwhelmed by the research that's coming out of JWST so far. But that's just because nobody's done the science yet. They've just, they're just sort of wallowing in the data right now, but they haven't gotten around to actually writing their papers yet. When they write their papers, this is what it feels like.
Yeah, and I'm really grateful for the early science release program, and I think that was a very wise decision, because being able to have these results within 5 months of launch is amazing. And we're actually talking papers, so it's not just here's an image, we kind of did like a little mini spectrum and aren't you excited, and it's like, no, here's this entire atmosphere, and there's still more we can learn about it, but we're just it's amazing what they've managed to find so far.
Paul, you're an exoplanet fan. What did you think about? Did you work on any of this? Or
no, I haven't. I'm sitting back and just like letting it kind of wash over me. What's really exciting about this, and I think this is correct, that in that spectrum, that is the first time that scientists have been able to confirm the presence of photochemical reactions in the atmosphere of another world. And the reason that is important is because it's a route to developing chemistry and chemical species that we might not otherwise get. For example, we know that photochemistry is super important in the atmosphere of Titan because it generates a lot of the long chain molecules we see there. It also is a thing that we think plays a big role in Venus's atmosphere. And Venus is you guys have heard me go on about Venus, you will hear again me go on about Venus, but it is the archetype world to understand the other fate, or one of the alternative fates that can befall Earth. Understanding Venus's atmosphere is critical for making sense of Earth-sized exoplanets. Now, WASP 39b is not an Earth-sized exoplanet, like Beth said. It's a hot Saturn. But the fact that we can begin to resolve chemical species that have got to be created as a function of sunlight is really exciting. I don't think we didn't think we'd see this. I don't think this is unexpected insofar as a phenomenon in the universe. But to detect it for the first time is a huge finding.
And that sulfur dioxide, like that is what you see in Venus, right? With the carbon dioxide and the sulfur dioxide.
Absolutely. It's
just a hot Jupiter.
Yes, exactly that, yeah.
And another thing about this is that because this is a planet that is a hot Saturn, it is in close to its parent star, we're actually able to sort of start building models on how that star's activity affects the atmosphere of this planet. Right. So that's also another piece of the puzzle that we can finally look at and say, like, okay, what does this actually mean when you have a planet that's that close in? Because all we have is Mercury, and this is closer in than that.
Yeah. Right. Yeah, I mean, that idea of being able to see the chemistry, and maybe when you take a planet like Saturn, but you bring it close to the star, and maybe maybe the star has different, the photons are coming in different wavelengths than what we have with the sun, you're going to get this weird chemical reactions that we just don't see here in the solar system, which leads to all kinds of really interesting outcomes. It's like, just to think that we're at this time now that we can analyze the atmosphere of multiple exoplanets, like not just that we know of 5,000 exoplanets, we are now analyzing the atmosphere and studying the chemical processes, the atmospheres, the cloud patterns.
It's the first real hint to what makes up these other planets.
Yeah,
and when I tell my students, up until really the mid-90s, we had no evidence for planets orbiting other stars. So in the time since we've had Windows 95, up through today, when there's now 11, which is my computer's trying to push on me. We have gone through this era. Like we said, we are now looking at the chemical constituencies and reactions in large planets, which means presumably the next 10 or 15 years, we're going to start making these advances for smaller worlds. And this goes back to the point you made, Beth, right? But looking for potential biosignatures, or who knows, even technosignatures in the atmospheres of large rocky worlds. I mean, what a time to be alive.
Yeah,
right?
and I mean, this helps us build that possible catalog. You know, what does this combination of molecules represent in the life of the planet? What does this combination represent? If we, look at Earth from a distance, what does that catalog tell us? Now, how do we compare that? Because we'll actually have things to compare it to, instead of just we got one planet. We had a couple others that we know stuff about, but nothing else in our solar system has really said there's life. I mean, we're looking underneath ice at this point. So
yeah, so great. All right, let's move on. Paul, hit us with your partial solar eclipse.
Okay, so this is not the first time we've seen this, but I think it's a really neat example, and I think it might be the first time Perseverance has seen it. So Mars has 2 moons. Now, you all may know that I have a pretty low regard for Mars. It's not that interesting. It's a planetary embryo. It's pretty small, and it has these 2 space nuggets that go around, and we don't know where the nuggets come from. Are they debris or whatever, right? Anyway, what is interesting is that occasionally they cross in front of the surface of the sun, and a few days ago, Perseverance managed to snap Phobos crossing in front of the disk of the sun, and it makes these kind of weird googly eye pictures. And you can see the fact that it is potato shaped. I mean, you can see that this is the shape of Phobos, and it is in a regular body. It is not in what we call hydrostatic equilibrium. Now, a few people have asked, does this count as an annular eclipse? And I guess technically this picture does. A partial eclipse, at least we use that nomenclature on Earth, is when the part of another occluding body, the moon in our case, takes a chunk out of the sun. Part of the image sequence that Perseverance returned shows Phobos taking a bite out of the sun, and then pictures like this have Phobos right inside the sun. So technically speaking, for the time that it was like this, crossing within inside the disk of the sun, it was an annular eclipse. The rest of the time it was a partial eclipse. I think calling it a partial solar eclipse is fine. What is telling is that we can find these kinds of images. We can see solar eclipses from the surface of another planet. This is wild to me. But I think more than anything else, what this drives home for me is that weird cosmic coincidence about the fact that the moon is about 400 times smaller than the sun, but about 400 times closer. And so in this epoch, we can have total solar eclipses. That is not a phenomenon that is possible on Mars today. And in the future on Earth, it won't be possible either, because the moon will...
But it will be possible in the future on Mars, because Phobos is spiraling inward.
So here's a question. I don't know if that's true. I don't know, because I don't know where the Roche limit is compared to where it needs to be for its angular size to occlude the sun completely.
But it doesn't matter. So as long as the moon orbits the planet faster than the planet turns on its axis, then the tidal interactions will pull it inward and speed up the rotation rate of Mars.
Right.
And so Phobos is doomed. It's got somewhere between 10 and 50 million years left.
Right.
And so an equally weird happenstance is that we're here at a time when Phobos exists.
So this is the question. I don't know where the Roche limit is in terms of the angular size of Phobos. Will it ever get close enough to fully occlude the sun before it's torn?
Before it tears apart. Interesting.
Or will it never get big enough and it will form this ring? But you know what? If we were really serious about it, we could accelerate the process. I'm just saying we don't have to wait 10 million years.
Right.
If we get serious about it, we could try and speed things along, maybe with some engines.
I mean, we've already done that with an asteroid, so an asteroid moon. So
you just knock something into Phobos,
yeah,
DMOS maybe, right? Or put up some engines on it. I think we could, if we were really serious, wanted a big techno project to bring the world together, why not just go and push Phobos into Mars's Roche limit?
So you like that idea better than my idea of pushing Venus into the sun?
That's a terrible idea.
I thought you might not like that.
Terrible idea. I don't mind if you could throw Mercury to the sun, but you could also, you know what I keep saying, by the way, if we're serious with Mars,
leave Mercury alone.
Hey, listen, I have named things on Mercury, but I also recognize that if we have to sacrifice something, the delta V is the minimum, is the lowest we'll need for Mercury. It's already there. It's already halfway down.
Yeah.
But if we were
easiest challenge,
Mercury is how we build our Dyson sphere. So
yeah, there's a lot of iron in Mercury. There's like a weirdly large amount of iron in Mercury. So
extremely weirdly large amount of iron.
Yeah.
But it's still not enough to build a Dyson sphere. Sorry, Fraser.
We can build a Dyson.
A Dyson swarm. Yeah, just a swarm. I don't need a sphere. I just need a swarm.
Oh, fair enough.
Yeah. All right. Let's still, it's very exciting. Let's move on to this amazing asteroid prediction that was made, Beth.
Yeah, this is really neat. So if you were on social media over the weekend, whatever social media you are currently existing on, you probably saw some images of this meteor coming in over southern Ontario. The really cool thing about this is that this was actually an asteroid that was detected on the evening of the 18th, which was Friday, and it came in on Saturday, early in the morning. But there was a whole bunch of, it starts out with the Catalina Sky Survey, who's all, hey, we found an asteroid, and they report it to the Minor Planet Center, who's like, oh, cool, put it in their database. And then NASA's Scout program automatically grabs it and pulls the data and starts looking at it to calculate stuff. And then you get amateur astronomers in Kansas, of all places, involved, and more observations taken of it. And eventually they were basically like, here's where it's going to come in. Here's where it's going to, what time it's going to come in. And they knew about it within 2 hours of it actually entering the atmosphere, which is amazing, because that means that all the scientists who were available and in the area could now turn all of their instruments and cameras in a specific place, specific time, and go, let's capture it. And there's tons of data that's probably going to come from this. And a bunch of people have been reporting sightings to the American Meteor Society, which, again, I will plug. If you see a fireball, go to the American Meteor Society and report that you saw a fireball. And now the scientists are asking for residents around Niagara to look for some of these meteor fragments. Mm-hmm. So meteorites probably made it to the ground. It was big enough that it probably left some pieces. It broke up in the atmosphere. It is, however, kind of on the edge of a lake. So, and there was snow. So this is a challenge. So they're asking residents to help them by finding stuff, and you can choose to keep it or you can choose to share it with the science team.
Share it.
Wait, I'm going to say share it.
Please share it.
I like my meteorite fragments, but they have already been analyzed.
Yeah.
And so this is only the 6th time we have tracked an asteroid coming through our atmosphere.
And I mean, this really has a potential to save lives. We saw with back in Russia in the Chelyabinsk event that thousands of people were sent to the hospital because they were looking out their window when this giant meteor exploded in the atmosphere and shattered the glass and lacerated all of these people. This was a 1 meter asteroid, very small, while Chelyabinsk was house sized. And with this, they got 6 hours of notice and they pinpointed exactly where it was going to hit. They could warn everybody. Everyone's phones could go off and say, stay away from windows. But they knew a 1 meter object wasn't going to be an issue. But they would have detected a Chelyabinsk days out, maybe even weeks out. And you would have had plenty of notice to know exactly where this thing was going to hit and the precautions to take.
Difference here, and I just want to preface this, is that the Chelyabinsk meteorite came in from the sun-facing side, so it was hard to detect in the first place.
Yeah.
So it's very difficult to detect small things when you're looking at the sun. So that is one of that's why Chelyabinsk was actually on the scale of scarier.
Right, but you got this automation. You got the detection made, the announcement sent out to all the right people, follow-on observations made by other telescopes. And you got this pinpoint accuracy figured out. And it's just a stunning, I think, piece of coordination and work on everybody involved in a great test run of this.
And one thing that was really exciting is a paper came out in the last week or two about a similar find, a fall and find in the UK. And one of the massive benefits of that sample is that it's not sitting out on the ground all that long.
Yeah.
So you can get, for example, at the primordial water molecules inside that object, and to tell you, you can actually learn a lot about the protoplanetary disk because it's not contaminated by the conditions on the Earth's surface if it's not there for very long. So being able to get scientists out there, even if it's a very common asteroid, it's still a sample from the solar system, and it's extremely valuable to get it quickly.
So like, Nick, how quickly do you want to get a sample? Like if a meteorite falls, how quickly can it get contaminated?
It depends upon what it falls into is one of the big questions. So one of the most productive meteorites we study for looking at organic water in the early solar system is the Tagish Lake meteorite. And that sounds like it would have been a good one because it fell in a lake, except it was a lake in British Columbia in the middle of winter that had most of the snow swept off of it by wind. So it fell on nice solid sheet ice. So it wasn't interacting with the ice particles around it. And there's a guy who's an amateur meteorite hunter who knew what he was doing, had gloves, had bags, had aluminum foil, went out and collected these things. Now, pro tip, aluminum foil's not great because it will react with the meteorite a little bit and cause problems. But the plastic bags and the gloves was awesome. That's what kept him from contaminating it. And then he kept it in a cooler on dry ice, which is perfect because isolated bag, that's not going to exchange carbon, it's not going to exchange anything. And it keeps it a lot closer to the kind of cold that you'd expect in space. Not as cold as that, but cold enough that not a ton happened to it.
So getting those like meteorite strikes collected correctly, quickly is vital.
Yes. You have, depending upon where and how it lands, a couple of days. The moment it rains, you're done. The moment there's a decent snowfall, you're done. It may as well have been a find that was sitting there for 100 years. Well, okay, that's an exaggeration. But in terms of collecting organics, looking at water, like, you're done. It's outside of scope. The moment it rains, the moment there's snowfall on it, or if it falls in a river or a lake or the ocean, God forbid, you'll never find that. And actually, one of the really hard things is even when we have this kind of data to say exactly where it's coming from, exactly where it's going to shoot through the sky, the last part of that process is darkfall. It's no longer going fast enough to make a fireball. It's just a dark rock falling out of the sky. We don't know the size, we don't know the shape, we don't know its momentum, we don't know the air currents well enough. That's why there's this big area that says there could be pieces anywhere in this. We have no idea.
Yeah.
Now, many times in the past when we've seen some of these fireballs come in and we've got them from multiple different angles, we can really compute this is exactly how it came in. We still can't find the darn thing because that uncertainty is so wide that, well, all right, how many farmers' fields are going to comb through looking for every pebble that doesn't quite belong?
Yeah.
To say nothing of the fact that there are so many things that could be meteorites that are not.
Yeah.
Right.
Go looking, you'll find.
There are a lot of meteor wrongs in this world.
Yeah.
But you gotta wonder, like, how many of them there really are. Like, when you're walking along, chances are you're always within, 6 feet of a meteorite, just like you're always within 6 feet of a spider. But you can't tell because it just looks like a rock.
I'm not going to go out and say that it goes quite that heavily concentrated because once it's sat on the Earth for a while and had a chance to like incorporate in a stream, been a little weathered, it's not really a meteorite anymore.
100 feet? A kilometer? But
I don't know the number. It depends on what size you're talking about. Like, there are micrometeorites everywhere. You're breathing meteorite dust right now.
Right, they're on the roof of my house right now. I couldn't bother going to get them. So.
Yeah. I did an interview with somebody who does that. It was really fascinating.
Oh, it's horribly fascinating.
Yeah. All right, last story, Nick.
Woohoo! I get to keep talking about rocks. So,
I mean, for as long as Paul lets Mars exist. Yeah.
You have months anyway, at least.
Please don't destroy it, at least until the RTGs run out. So, one of the things that we went to Mars to look for is habitable environments. And one of the key factors on that is evidence of sustained, long duration water. Now, one of the debates we keep running into is, okay, we've seen evidence of river features, fluvial features. We've seen evidence of lakes, but we don't know how sustained that was. We don't know how much water was really there. Was it a thin brine? Was it a deep crater depth lake? Like, what was it? So one of the things that we selected with Jezero Crater was this great big river delta on the inflow side. Jezero has both an inflow and an outflow, which is very different from Gale, which, yeah, has small inflows. It has no outflow, at least that we can identify in any believable way at the moment. So we've been driving towards this delta for a lot of the mission, and a lot of the rocks that we've seen on the ground are what we call ventifacts. They're these nice, sharp, pointed rocks. And that's evidence of something that was difficult to weather, so it held up to the elements for a long time. But it's just being bombarded by wind for hundreds of thousands or millions or even billions of years to make these really sharp points. And so that's commonly what we see in these boulder fields. Well, just in the last couple days, some of the raw data has come down, but JPL hasn't actually even published a press release about this. I gotta thank my Twitter friends for, cluing me into, hey, this is neat. We found rounded cobbles in the delta. This looks like an honest-to-God conglomerate. That, by the way, is the usual boulders we see. These are the ventifacts with those sharp angles all over it. That's what the delta looks like from a distance. One more over. The really terrible image. That is the remote image from I'm so used to Curiosity. From SuperCam, zoomed all the way in. These are cobble-sized objects. Those are rocks, not rocks. And they're rounded, and there's a great big pile of them. This tells us we didn't just have a little bit of water, we had enough water to move those. You start thinking about something like the size and scale of a braided stream in the mountains. That's what's moving rocks this big. And this is a delta, so it's not normally the kind of thing you'd associate with a braided stream, so it's probably even deeper than that. This is significant flow, and it's transporting these rocks for a long distance to make them this kind of rounded.
And so then stuck in mud
stuck in mud, which also speaks to, there would be some seasonality or something that changed the average grain size that was moving through that. So you deposit the cobbles, then you leave all of the silt and sand and other sediments that combines that together and makes that conglomerate. So we're actually seeing just really solid, geologists speak, fluvial process, stream process.
I'm so familiar with that kind of rock here where I live. We have this stuff everywhere. It's
all over BC. It's some of my favorite hiking area. Just don't turn your ankle.
Yeah. So you have these, they look like, I don't know, the skin of a toad, but it's like different colored rocks, all blobbed around, collected with this mortar of sandstone. And then over time, the mortar melts away and these rocks pop out of this exposed stone and they turn into these rocky beaches that we have everywhere.
So this is exactly what I'm talking about, where you have rock, what Fraser's calling the toad skins, that are sitting there, and those are the cobbles, the big pieces that just didn't want to break down easily. And then that gets mortared together with this little bits of sand and finer sediment that sticks it together into a rock. Well, that fine sand is much more easily removed than the big cobble, particularly by things like, wind blowing on it for billions of years.
That's so cool.
And so these cobbles slowly come out of the rock and roll downhill.
Well, I hope they are going to put a press release. If not, we're going to have to report on this from the raw data, but it's definitely exciting news. Good job, Nick. Do you want to write this up for Universe Today? I can pre-approve the story right now.
Sounds great. I'll get that done sometime in the next 9 months.
Nice. We might need a little quicker turnaround. All right. So we're now going to shift to the interview portion of the episode. But before I do, I'm going to say goodbye to the co-hosts who joined us this week. they are free to shut down their window and enjoy the rest of their evening while we struggle through this final interview. But I want to give them a chance to shamelessly self-promote what they're working on. Beth, what are you working on, and where can people find out more?
We are, wow. You can find me at Planetary Pan basically on all the things. I am on the tech.lgbt Mastodon server. So if you need that, that's where my new place is. I'm reviving my Tumblr blog because reasons.
Did you hear that they're federating Tumblr together with Mastodon?
Possibly Flickr.
Oh man.
Yeah, it's going to be pretty cool. And then working on some SETI stuff, really. So we have more stuff coming. Next week is Giving Tuesday, and I'll be interviewing Anne-Marie Cody about detecting technosignatures.
Very cool.
So you can find, for better or worse, I'm sticking with this flaming dumpster that is Twitter for the time being. I don't have the bandwidth to go and set anything else up, and what I've seen, I don't have the capability of understanding how Mastodon works, at least not right now. So find me at the Planetary Guy at Twitter, where I will be shitposting about Mars.
It's not that hard, and I'm having a lot of fun. Like I was definitely exhausted. Like I am utterly platform exhausted at this point. When I think of how many times I've had to package up all of my stuff and move to a new home, but I really like Mastodon. I like the federatedness of it. I like the way it's being interconnected, how easy it is to pull data in and out. I just need all of my friends to show up, which is why I'm hard selling you on this, Paul.
I will give it a go. I'm
give it a go. Yeah, if you need someone to walk you through this step by step, I'm there for you.
And I can help you as well.
And Beth too. And you don't have to make this a I don't like that bird site guy. It's just about having a backup.
Sure,
it's a lifeboat. You only need a lifeboat when the ship is sinking.
Yeah. So my plan right now is just been to jump overboard and hope for the best. But I'll take
exactly. So
I'll take
let's at least give you a lifeboat. Nick.
And Fraser forgot to mention, but Astronomy Cast is now on Mastodon as well.
Oh, great! I should follow that. Okay, nice. Nick.
I'm the wandering scientist, and it's more important what my wife is up to than it is what I'm up to. You might not see me much in January because there may be another screaming member of the Castle family that appears. So hopefully this won't be my last episode, but it might be my last one for a little while.
We'll send our congratulations, because that's amazing.
Thank you.
Yeah.
But you can find me on the flaming dumpster fire that is Twitter, because I just started figuring out, by golly, and then it got bought.
I just found your wandering scientist handle and followed you just like a couple of days ago.
I finally broke 30 followers. Like, come on. It's funny too, because I tried to sign back into Facebook. Next day it's down for an entire day. I finally start figuring out Twitter and using it routinely. Musk finally buys it after 9 months of no, I don't want it.
Yeah.
I'm afraid that wherever I go, it's going to crumble when I get there.
All right. We should wrap things up. We've got to get to the interview portion. So I want to thank my co-host for joining me today. That was super fun. Thank you to Nancy and everyone from the WSH crew for organizing things behind the scenes. Thank you to Pamela, as always, for engineering the show. We couldn't do this without you. Thanks, guys. You're free to close the window, and we will now fight through engineering this last interview portion. Pamela, you ready?
Fraser.
All right. Thanks, guys. Great to see you again. Oh, so this is how we're going to do this? Okay, this works. Nicely done. I like it. All right, so my first question is, of course, who are you and what do you do? So let's get started. Who are you and what do you do? All right, what did you discover? Oh, is there an audio issue? No crap, no sound from me either. So you're hearing me, but not the guest. Okay.
By the ancient astronomer Hipparchus, who was active a little over 2,000 years ago. And it's the earliest star catalog in human history, in the sense that it's the earliest attempt to precisely measure coordinates for all visible stars, visible to the naked eye.
And so we don't actually have a copy of any of this stuff. So how do we, like, it was all just referenced by Ptolemy. And I go on for quite a while here.
That's correct. It was lost presumably already in antiquity, because Ptolemy's star catalogue, which was composed a few centuries later, took precedence over Hipparchus's. And in antiquity, for a work to survive, it had to be copied regularly every few centuries. So if there wasn't enough motivation, they just naturally disappeared.
How do we know that it was Hipparchus?
Well, it's a collective discovery. In March of 2021, Peter Williams, one of the co-authors, reached out to me because he had found in a palimpsest, that is a recycled manuscript of parchment, some numbers and the indication that these were degrees. And this was in an astronomical context, so he supposed that these were star coordinates. He wanted to have my opinion. And I immediately thought of Hipparchus because the coordinates didn't match with what we know of Ptolemy's star catalogue.
So
then we went forward and continued deciphering the text.
So were there specific measurements in the document that proved that it was Hipparchus, like the age of when the measurements were
Over
made?
time, in the course of centuries, there is a phenomenon called the precession of equinoxes, so that the positions of all stars shift by, a little over 1 degree in a century, very approximately. So based on that, you can compute what time the coordinates are valid for. But this isn't what I meant by the things didn't match. We would actually compute and see that even accounting for this time difference, the coordinates didn't match, so they must have come from a different source than Ptolemy.
So why did people overwrite texts?
Yes, we literally have thousands and thousands of palimpsests, as they're called, in all major libraries. Parchment was an expensive material, and it was also remarkably durable, so it made a lot of sense to erase parchment and write over it. Whenever a text was not considered uninteresting or just redundant, it could be a good candidate for being erased and recycled.
And is searching through these older texts something that's commonly done today?
That's a good question. What the Museum of the Bible decided to do when they acquired this manuscript, they organized a series of multispectral imaging campaigns. And multispectral imaging is a technology that can literally reveal things, text, that is invisible to the naked eye. So that's what they did. It requires work to capture the images, then there's image processing, and we scholars come in at the back end to try to read what is on the images.
Now, were you specifically searching for work from Hipparchus?
Yeah, I should say I didn't expect such a discovery to happen in my lifetime. So when I realized that I was going to be a part of it, it was very exciting. But But we had to remain cautious because it wasn't immediately obvious that this hypothesis was right. It was just a hypothesis to begin with, and then it took us literally months to decipher more text, and as we recovered more coordinates to really solidly establish that these coordinates really fit for the time of Hipparchus. And then we had a further argument that one of the coordinates for Ursa Minor is actually quoted by Ptolemy for Hipparchus, so that was further confirmation. And finally, another feature that pointed in the same direction is the use of equatorial coordinates, which is common in today's astronomy, but the star catalogue of Ptolemy, and indeed all of his star measurements, are generally in ecliptical coordinates, which is another reference system. So this also took us a while to confirm, but it all made sense at the end.
Hipparchus was considered like one of the fathers of modern astronomy. And so in looking at these ancient texts, what does that really tell us about the birth of science itself, being able to see this directly?
That's a good question. I haven't been asked that yet. Let me think. I'm always cautious with characterizations of someone as the father of history or astronomy or whatnot. Hipparchus was heavily indebted to his predecessors, especially the Babylonians, but also Egyptians and Greeks, who had made so many contributions. But this is a very interesting document of the birth of science, because Hipparchus is part of that movement which happened over centuries and over several different cultures and linguistic areas. We can really see in this document the turn towards measuring and really quantifying the world surrounding us and its laws. So in that sense, it's a huge step forward for the birth of science.
How did Hipparchus make such accurate measurements so long ago?
So one thing that's remarkable is how accurate he managed to be with naked eye observations. He probably was as accurate as possible using no magnifying elements. He may certainly have had instruments such as what the Greeks called a dioptra, which is a sighting tube with some paraphernalia to help the astronomer focus and register the coordinates. He may have been using armillary spheres. We know that other astronomers did in antiquity. More generally, it's also very interesting to think in terms of cultural and social setups. Was he working alone, or did he have collaborators, perhaps slaves? Did he benefit from patronage, from institutions, from the monarchy, or from other social institutions? These are a lot of open questions, and really this new material, I think, will encourage people to get more interested in ancient astronomy. At least that's what I hope, and there are just so many fascinating questions to answer.
How much of Hipparchus's observations were in this one document that you found? I guess I had a longer version of the question.
It is a small sample. In total, we have coordinates for 15 stars out of presumably around 1,000 stars. We know that Ptolemy's catalog contained a little over 1,000 stars. That's about as much as you can see from Greece with the naked eye. So there's reason to believe that Hipparchus had also 1,000, maybe less, but in any case, this is 1 or 2% of the total. Now, we do have some ideas of places to look for more fragments.
So where could you look for the rest?
Well, in the manuscript, the Codex Climaci Rescriptus, some pages have not yet revealed their text. So we hope that by more imaging, more image processing, and more scholarship, we can recover that text. And some pages in particular, because we can reconstruct the sequence of contents in this erased text, there's strong reason to believe that some pages do contain the coordinates. We just need to tease them out. The second place to look would be in St. Catherine's Monastery on Mount Sinai. There is a a history of research and multispectral imaging by the Early Manuscripts Electronic Library at Mount Sinai. And so that would be a very exciting place to look. They may have reused pages in other manuscripts that are still extant.
Where does this discovery go next? I guess that's a fancier version of it.
It's such a tiny fraction, and that's a really important question. It is somewhat costly in terms of equipment, in terms of work time to do this, but clearly the rewards can be breathtaking in terms of the historical evidence we recover. So I really hope that this discovery leads to more large-scale multispectral imaging of palimpsest. There are literally thousands, and only a tiny fraction have been imaged.
What other missing texts would you like to find?
Wow, there are so many. I mean, more pages from this star catalog would be amazing. But, you know, the philosopher Aristotle, most of his works are lost, for instance. So it would be nice to have some more of that, for instance. In terms of ancient science, you know, the Elements of Euclid, this great mathematical textbook, was a compilation of earlier works. So it would be nice to have, you know, the mathematics of Eudoxus of Cnidus, for instance, or other great figures. I mean, my wish list would be infinite because really we've lost so much.
All right, now I showboat for a while here, but so we're learning more and more about how skilled the early astronomers were despite their modern equipment. Do you think that we will discover more about ancient astronomy? And this is the last question that you won't hear me speak, because partway through his answer, you notice that I realize that my audio has been muted this entire time, and I fix it. So we'll discover more about ancient astronomy. Like, I really had a lot of interesting things to say, clearly. And I just go on and on and on. Man, lost.
Well, I think in the past century, we've drifted a lot closer to the reality of ancient astronomy. There have been milestones. There's been, for instance, Otto Neugebauer's great monograph of 1975, A History of Ancient Mathematical Astronomy, which was an unparalleled effort to just assess comprehensively all of the extant evidence. There's been Alexander Jones' more recent work, especially his publication of all the astronomical papyri from ancient Egypt, which weren't available to scholarship or to the public before his work. So that really went to show that there were a lot of other astronomical traditions besides Hipparchus and Ptolemy and the few great names that we know, and that ancient astronomy was much more diverse.
There it is.
So, you know, one big issue about Ptolemy has been, was he committing plagiarism and copying Hipparchus's catalog completely without acknowledging how deeply indebted he was. Our study is able to refute that definitively. I mean, it was never a consensual claim that Ptolemy was doing plagiarism, but we can show now that some of the coordinates in Hipparchus's catalog, they just do not match with Ptolemy's. Even if Ptolemy adjusted for precession, he was using other sources, maybe other catalogs. So now that we know that there were all these exciting other traditions of ancient astronomy, or maybe Ptolemy's own observations. So that's one instance where, by careful scholarship and close reading of the texts and, you know, careful consideration of the evidence and always looking for more evidence, we can actually get a little closer to reality.
That's really cool. Well, Victor, congratulations. It's an incredible discovery and addition to our history. And I look forward to more of these documents surfacing. It would be crazy to read Aristotle's original writing and others. Very impressive. Thank you so much.
Thank you. Thank you very much for having me.
All right. That's it. Now we're done. Thanks, everybody. Thanks, Pamela. And we'll see you all next week.